Hello everyone, welcome to this video. I am Akshay Jain and you are watching 13th video of data science series. Uh, in this video, we'll discuss part 4th of our assignment, which is regression models and implementations. In this video, we are going to discuss question 7th and question 8th. Let's proceed. Let's see the question 7, which is about linear versus logistic regression. Asks us to compare and contrast linear regression with logical logistic regression, understanding when to use each and how they differ fundamentally. So let's see linear regression first. The purpose of linear regression is to predict continuous values using linear relationships between variables. The hypothesis function is y equals that 0 plus that 1 times x, representing a simple linear equation. The output is a continuous value. It can be any number, positive or negative, with no bound. The cost function we minimize is mean squared error, or MSE, which measures the average squared difference between predicted and actual values. Common applications include outprice predicts based on features like square footage and location, temperature forecasting, or stock price prediction. Linear regression works best when the relationship between input and output is approximately linear. Logic Logical regression is different. It's used for binary classification, not regression. Despite its name, the purpose is to predict class probabilities. Instead of a linear equation, we use a sigmoid function. H of x equals 1 divided by 1 plus e to the power of negative z. The sigmoid function squeezes any input value into a probability between 0 to 1. An output of 0.7 means 70% probability of the positive class. The cost function used in cross entropy loss, which is more appropriate for probability predictions than mean squared error. Applications include a small spam classification, predicting if an email is spam or not; disease detection, predicting if a patient has a disease and a credit approval; predicting if an applicant is credit worthy. Logistic regression creates a new non-linear decision boundary, making it more flexible than linear regression for classification. Linear versus logistic regression. Let's see the comparison between them. Let me assume the key difference is linear regression produces continuous output values with no bounds. Logistic regression produces probability output constraint between 0 to 1. Linear regression uses a linear decision boundary, a straight line separating classes. Logistic regression uses a non-linear decision boundary, a curved line that can better separate complex patterns. Linear regression minimizes the mean squared error. Logistic regression minimizes cross entropy loss. Linear regression solves regression tasks predicting continuous values. Logistic regression solves classification tasks predicting discrete classes. Both are fundamental algorithms, but they are designed for different types of problems. Let's see gradient descent optimization. Both algorithms use gradient descent for optimization. The update rule is theta becomes theta minus alpha times the gradient of the cost function with respect to theta. Here alpha is the learning rate, uh, hyperparameter that controls how big each update step is. The gradient is the direction of steepest increase in the cost function. By moving the opposite direction, negative gradient, we minimize the cost. The algorithm updates parameters iteratively, making small steps toward the minimum. Eventually, the parameters converge when the gradient becomes very small. If the learning rate is too small, convergence is very slow. If it's too large, the algorithm oscillates around the minimum and might not complete. Finding the right learning rate is important for effective training. Now let's proceed to the question 8.